Everywhere you look, something is turning. The earth rolls beneath your feet, silently spinning toward dawn. The moon circles above, locked in its eternal waltz. The sun drifts around the galactic core, dragging a billion worlds in its invisible wake. Even you, sitting still, are moving faster than you could ever imagine. Rotation isn't just motion, it's the pulse of existence itself. From the largest galaxies to the smallest particles, the universe never sits still. Everything whirls, swirls, and spirals. It's as if the cosmos is performing an ancient dance, one that began before there was even light to see it. But why? Why does everything spin? Why not a universe of stillness, of frozen perfection, where matter rests in quiet symmetry? Because stillness, as it turns out, might be the one thing the universe refuses to allow. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum. And let's ease into tonight's journey together. Long before stars were born, before the first atoms fused, there was chaos. The newborn universe, fresh from the Big Bang, was a storm of energy. Not yet space, not yet time as we know it, but a boiling sea of possibilities. And within that chaos, imbalance was born. Some regions carried slightly more energy than others. Some points expanded, just a fraction faster or slower. These imperfections were tiny, the kind of fluctuations so small they seemed meaningless. But those differences were seeds. Seeds of structure, seeds of motion. Because once imbalance exists, motion follows. Energy begins to move from one place to another, chasing equilibrium, though it never quite reaches it. These flows created ripples, and the ripples began to twist. Imagine stirring cream into coffee. The liquid doesn't just mix, it swirls. Whirlpools form, vanish, and form again. The same happened on the grandest possible scale. In the early universe, as matter cooled and expanded, it began to clump together. And in those clumps, spin emerged naturally. A universe without rotation was never an option. From the moment energy became matter, the dance began. Look at the night sky, and you'll see order, constellations that seem fixed and eternal. But that's an illusion. Behind that stillness lies motion so vast it becomes invisible. Our planet spins once every 24 hours, fast enough to fling you into space, if not for gravity's firm grip. The moon pirouettes around us once a month. The Earth traces its 584 million mile orbit every year, while the entire solar system hurtles around the Milky Way at 500,000 miles per hour. And yet, silence. We don't hear the motion. We don't feel the turning. To us, the world feels still because everything around us spins together, locked in the same rhythm. We're like dancers in a dark room, unaware of our own steps because the floor moves with us. But the rhythm is there, unbroken, unstoppable, universal. Spin gives shape to everything. Planets aren't perfect spheres. They bulge at the equator, squeezed by their own rotation. Storms spiral because of the planet's spin. Even galaxies, those colossal cities of stars, take their elegant spiral form because of rotation. Without spin, the cosmos would be shapeless. Stars would collapse too quickly. Planets would form unevenly, tearing apart under their own gravity. Even atoms, the building blocks of matter, rely on a kind of rotation at the quantum level, a property scientists call spin, that defines their behavior and their very identity. Every level of existence carries the same signature, a twist, a turn, a rhythm. It's almost as if the universe can't help but express itself through motion. There's a quiet irony in all of this. Motion is stability. Think of a spinning top. As long as it spins, it stands upright, defying gravity. The moment it slows, It wobbles and falls. The same law governs the cosmos. The planets stay balanced in their orbits because of their motion. The stars resist collapse because their internal forces, born from rotation, counteract gravity's pull. Stillness, by contrast, leads to decay. The universe abhors rest. If everything stopped spinning, gravity would win. The delicate balance holding everything apart would crumble. Planets would crash into their stars. Stars would implode. Galaxies would unravel. Spin, in its quiet persistence, is life itself, the act of defying collapse. If you could step outside the universe, beyond time, beyond matter, and watch it unfold, it might look like an enormous dance floor. From a God's eye view, everything would move in sweeping arcs and graceful circles. Galaxies would twirl like glowing pinwheels. Stars would orbit in slow, deliberate paths. Planets would glide around their suns, and moons would trace smaller orbits, each locked in a perfect step. And the dancers never miss a beat. Each motion follows laws, not written by hand, but by the very structure of reality. Angular momentum, conservation of energy, gravity's embrace. Together, these laws choreograph the entire show. Every spin we see, from the swirl of a hurricane to the rotation of a pulsar, is a reflection of that invisible order. We often speak of the universe as chaos, a storm of random events. But rotation hints at something deeper, something patterned. Why should chaos move in circles? Why does turbulence produce spirals, not splatters? Because motion, when left to itself, finds the most efficient path, and that path is rarely straight. In physics, straight lines are the domain of perfection, of no interference, no imbalance. But the real universe is full of interruptions. Gravity, pressure, magnetism, collisions. These forces twist trajectories, bend flows, and curl energy into loops. From that constant tug of war, structure arises. Even destruction creates beauty. A collapsing star, for instance, doesn't implode quietly. It spins faster, like an ice skater pulling in her arms, until it becomes a neutron star, spinning hundreds of times per second. Out of death comes motion. Out of chaos, rhythm. You are part of this rotation too. The atoms in your body were forged in the heart of spinning stars. The iron in your blood once flowed through a rotating nebula. The earth beneath you, the very ground, exists because cosmic dust gathered into a spinning disk billions of years ago. You are not separate from the motion of the cosmos. You are made of it. Every breath you take, every heartbeat, every thought is bound to that eternal turning. Inside your cells, microscopic motors spin to generate energy. Your planet turns beneath your feet, carrying you through night and day. Even the galaxy's motion ripples subtly through you, though you can't feel it. When you move, when you dance, when your heart beats, you're echoing the first cosmic rotations. A quiet remembrance of where you came from. We often look at the stars as if they are fixed, timeless beacons scattered across a still black sea. But if you could watch them long enough, you'd see them drift, spiral, and evolve. Every star you see tonight is moving. Every galaxy is turning. Every light in the sky is part of a greater choreography. Even time itself seems to flow in circles. Days, years, ages. Civilizations rise, fall, and rise again, like the orbits of worlds around their suns. History too spins. Perhaps that's why humanity is drawn to circular symbols, halos, wheels, mandalas. They whisper of something ancient, something eternal. The circle is the geometry of truth. No beginning, no end. Only motion, forever. Scientists can explain how things spin, through angular momentum, through gravitational collapse, through physics. But why everything spins? That remains a more profound mystery. Maybe it's not a question physics alone can answer. Maybe it's a signature, a cosmic fingerprint left on everything that exists. Because when we trace it all back, every rotation, every orbit, every spiral, we end up at the same place, the birth of the universe itself. That moment wasn't quiet. It was expansion, energy, chaos, and rotation. The first movement in the great cosmic symphony. The universe didn't begin with stillness. It began with motion. And perhaps that's the truth we've been circling all along. When you look up tonight, try to see the movement behind the stillness. The stars are not frozen. The universe is not static. Everything you see is spinning, slowly, gracefully, endlessly. From the swirl of galaxies to the invisible rotation of particles smaller than atoms, existence itself seems to prefer motion over rest. Because spin isn't just what the universe does, it's what the universe is. A dance that began with creation and will continue until the end of time. Or perhaps, as some believe, until it begins again. And you, tiny observer, standing under the turning heavens, are part of that dance. A single step in an infinite rhythm. Before there were planets, before there were stars, before even atoms had settled into shape, there was motion. Not the gentle, familiar motion we experience, the Earth's rotation beneath our feet, or the moon's orbit in the night sky, but raw, primordial movement, energy in its purest, most unrestrained form, the kind of motion that precedes order, that precedes light, that precedes time itself. This is where the story of spin begins. Imagine a void so empty, so profound, that it defies imagination. No galaxies, no stars, no matter, only a vacuum filled with possibility. And then, a spark, the Big Bang, not an explosion in space, but an expansion of space itself. Energy poured forth, spreading, stretching, accelerating. The universe was born in a surge of movement, every particle racing outward, every photon streaming across the newborn cosmos. And with that energy came imperfection. Perfect symmetry cannot produce rotation. Only imbalance can. Tiny fluctuations in density, microscopic variations smaller than the width of a proton, were enough. Those slight differences caused matter to begin moving, tumbling, spiraling. Motion was baked into the cosmos from the very beginning. Spin is older than light, older than gravity, older than matter itself. As the universe cooled, hydrogen and helium atoms formed. Clouds of gas drifting across the darkness began to collapse under their own gravity. And as they collapsed, something remarkable happened. They began to spin. Why? Because angular momentum must be conserved. If you're not familiar with the idea, it's simple. A spinning object will keep spinning unless acted on by an outside force. Collapse a cloud of gas, and the tiny initial motions, the subtlest twitches, get amplified. Picture an ice skater, arms outstretched, spinning slowly. Pull them in close, and the rotation speeds up. That's exactly what happened in those primordial clouds. The tiniest imbalance became the seed of enormous angular velocity. This spinning motion set the stage for everything that came next. Stars, planets, galaxies. Spin was the invisible sculptor, shaping the universe before we even existed. Within the spinning gas clouds, regions of higher density began to collapse into stars, and stars inherit their spin from their parent clouds. Some spun slowly, steady, and predictable. Others spun so fast that they flung material outward, shedding clouds of plasma that would later seed planets. Rotation determined the star's fate. Fast spin could stabilize it, slowing collapse. Too fast, and it could tear itself apart. Spin governs the rhythm of nuclear fusion, the balance between gravity and pressure, life and death of every star. Even the sun, which seems so constant and eternal, rotates. Around its equator, a single turn takes roughly 25 days, while its poles lag slightly behind. That differential spin affects solar storms, magnetic fields, and ultimately life here on Earth. Everything that follows, the warmth on your skin, the rhythm of the seasons, the cycles of climate, is shaped by stellar spin. From the residual gas and dust left behind by stars, planets form. And planets too spin. The same conservation of angular momentum applies. As dust clumps into rocks, rocks into boulders, and boulders into planets, the motion of countless fragments accumulates into planetary rotation. Sometimes it's gentle. Venus rotates so slowly that a single day lasts longer than its year. Sometimes it's violent. Jupiter spins so fast that its equator bulges, clouds streak into stripes, and storms rage for centuries. Rotation shapes planetary weather, magnetic fields, and tectonic dynamics. The Earth's spin gives us the Coriolis effect, steering winds and oceans, creating hurricanes, shaping deserts, guiding migration patterns. The day and night cycle itself is a product of this rotation, the heartbeat of our planet. Even life is attuned to this rhythm. Circadian cycles, biological clocks, reproductive patterns all follow the spin of the world. Our very biology is a child of rotation. Scale up and the pattern continues. Galaxies, massive cities of stars, also rotate. The Milky Way, our cosmic home, spins at roughly 500,000 miles per hour at its outer edge. But the motion is far more than a speed. It is a structure. Galactic rotation forms the iconic spiral arms, sweeping stars, gas, and dust into graceful arcs. These spirals aren't decorative. They are the highways of star formation. Regions of higher density sweep through the arms, compressing gas clouds, triggering the birth of new stars. Without spin, galaxies would collapse into chaotic clouds of matter. The beautiful pinwheels we see in the night sky, the very structure of the cosmos, owe their existence to rotation. Spin is not just macroscopic, it is fundamental. At the quantum level, every particle possesses an intrinsic spin, a property as essential as mass or charge. Electrons, protons, neutrons, all have spin. This is not literal rotation. It's a deeper, intrinsic property of reality that governs how particles interact, how atoms bond, how light behaves. Without quantum spin, chemistry wouldn't exist. Without chemistry, no molecules. Without molecules, no life. Spin, from the tiniest electron to the largest galaxy, is universal. It is a constant signature of the cosmos, a whisper of order in the chaos. Spin is rarely smooth. The universe is violent. Clouds collide, stars explode, galaxies merge. Each collision redistributes angular momentum, twisting matter into new forms. Some collisions slow rotation, some accelerate it, some tilt axes, creating oblique orbits, moons that spin backward, planets with odd rotations. Earth itself bears the scars of such violence. A Mars-sized body slammed into the young planet, ejecting debris that eventually formed the moon. That colossal impact also set Earth spinning at its present rate, creating the day-night cycle we know today. Chaos, it seems, does not destroy rotation. It reshapes it, perpetuates it, ensures that the dance continues. Every spin, every orbit, every rotation is a memory. The universe remembers its beginnings in the motion of everything within it. Even now, as you sit reading, the Earth rotates at 1,000 miles per hour. The solar system moves around the galaxy at 500,000 miles per hour. And yet, this motion is the fingerprint of cosmic history. From the Big Bang to today, motion has carried information about initial conditions, about interactions, about the subtle imbalances that shaped existence. Rotation is more than movement. It is memory encoded in the fabric of reality. There is something deeply philosophical about rotation. While most physical laws are time-symmetric, they don't care if time moves forward or backward. Spin gives a sense of direction. A spinning top tells us which way is up. A planet's rotation determines east and west. A galaxy's spiral indicates its orientation and history. Spin creates a subtle arrow in the universe, a narrative embedded in motion. Time flows, and spin endures. Every rotation from particle to planet is a silent testament to the passage of time and the persistence of energy. We often fail to perceive motion because we are embedded within it. We live on a spinning world, orbiting a spinning star, moving through a spinning galaxy, and yet we feel still. It takes perspective to appreciate the scale. It takes imagination to grasp that even as we walk, breathe, and sleep, we are part of a cosmic ballet spanning billions of years. Every rotation tells a story of creation, collapse, chaos, order. Every orbit, a line in the poem of existence. We are not observers of the universe's spin. We are participants. Every heartbeat, every step, every thought is in sync with the rhythm that began before we existed. Spin is everywhere because it had to be. It is a consequence of imbalance, of gravity, of physics itself. It is the universe's first law, its first song, its first movement. From quantum particles to galaxies, from planets to stars, everything that exists carries that signature. Spin is a bridge between chaos and order, past and present, life and the void. And the story is not over. Every rotation continues to shape the universe. Every collision spins new forms into existence. Every orbit tells a tale of survival and transformation. The universe does not pause. It spins endlessly, majestically, imperceptibly. And in that spin, it writes its story. And we, in our brief, fragile lives, are lucky enough to witness it, to feel it, to become a small part of that eternal motion. Gravity is often called the weakest of the fundamental forces, but in truth, it is the most patient, the slowest, and the most inexorable. While electromagnetism dazzles with sparks and nuclear forces rule the heart of atoms, gravity works quietly, persistently, sculpting the universe over billions of years. And in doing so, it has played a starring role in why everything spins. Imagine a cloud of dust drifting in the void. Alone, it floats silently, unremarkable. But place it near other clouds, and suddenly the story changes. Tiny attractions, imperceptible at first, begin to pull the particles together. Gravity does not rush. It gathers matter slowly, steadily, coaxing chaos into order. In the beginning, these forces acted over immense distances, drawing hydrogen, helium, and traces of heavier elements into clumps that would become stars and galaxies. And as matter coalesces under gravity, spin naturally emerges. The reason lies in a principle as immutable as the universe itself, the conservation of angular momentum. Picture a massive, irregular cloud of gas in the primordial universe. Random motions, tiny as they may be, exist within it. When gravity pulls the cloud inward, those tiny movements are amplified. A slight tilt or off-center motion turns into a whirl, a spin that grows stronger as the cloud shrinks. It's the same phenomenon we see with figure skaters pulling in their arms to spin faster. Collapse under gravity, combined with initial imperfections, produces rotation almost inevitably. Gravity is not merely a force of attraction, it is a choreographer, orchestrating the cosmic ballet, making rotation a natural consequence of structure formation. Within these spinning clouds, stars are born. Gravity compresses the gas until nuclear fusion ignites, and a star is born. Yet gravity continues to shape its spin. The star's final rotation rate depends on multiple factors: the original angular momentum of its cloud, magnetic fields threading through the collapsing matter, and interactions with nearby protostars. Some stars spin slowly, perfectly balanced, emitting steady light for billions of years. Others spin with dizzying speed, shedding matter and generating powerful magnetic storms. Gravity governs the tempo, dictating whether a star will be a calm beacon or a violent furnace. Even exotic objects like neutron stars and pulsars are extreme testimonies to gravity's power. When a massive star collapses under its own weight, gravity shrinks it to the size of a city, while spin rates can skyrocket to hundreds of rotations per second. A collapsed core becomes a cosmic lighthouse, beaming radiation with clockwork precision. Gravity does not merely allow stars to form, it imposes motion, dictates spin, and ensures that every star carries a signature of its birth. Planets form from the debris left over after star formation in swirling disks of gas and dust called protoplanetary disks. Gravity guides these particles, pulling them together into larger and larger bodies. But here's the twist. Gravity not only gathers matter, it channels spin. Collisions between planetesimals, the building blocks of planets, are rarely head-on. They often occur at angles, nudging the growing planet into rotation. Gravity ensures that spin is transferred, redistributed, and conserved across every collision. Even moons owe their motion to gravity. Tidal forces between planets and their satellites can speed up or slow down spin, lock rotations into synchronous patterns, and create complex orbital resonances. Earth's moon, for instance, keeps one face always toward us because of tidal locking, a dance choreographed by gravity over billions of years. Gravity is both the architect and the timekeeper. Without it, planets would drift as lifeless, motionless rocks. With it, they spin, orbit, and hum with life-giving cycles. Scale up once more, and gravity's role becomes awe-inspiring. Galaxies, colossal congregations of stars, gas, and dark matter, spin not by chance, but because gravity molds their structure. Dark matter, invisible yet dominant, forms massive halos that guide the assembly of ordinary matter. Gas falls into these gravitational wells, spinning faster as it collapses, forming the iconic spiral arms. Gravity ensures that the momentum of countless stars aligns into a coherent, rotating structure. Even galaxy collisions, seemingly chaotic, are dominated by gravity. Spin is redistributed, axes tilt, and angular momentum is conserved. Elliptical galaxies, irregular galaxies, and grand spirals all bear the imprint of gravity's hand, showing that even on the grandest scales, rotation is inevitable. Perhaps nowhere is the interplay of gravity and spin more extreme than around black holes. Born from the collapse of massive stars, black holes are gravity incarnate. They bend space-time itself, warping reality. Yet even they spin. Some rotate at nearly the speed of light, dragging space-time along with them in a phenomenon known as frame dragging. This spin affects the behavior of surrounding matter, shaping accretion disks, powering relativistic jets, and influencing the evolution of entire galaxies. Gravity does not simply allow a black hole to exist, it forces it to rotate, ensuring that the spin of the progenitor star, along with the angular momentum of infalling matter, manifests on the cosmic stage. Gravity's influence on spin extends beyond formation. Tidal forces, differential gravitational pulls, subtly adjust rotational periods and axial tilts over time. Consider Earth. The Moon's gravitational pull gradually slows our rotation, lengthening our days by a fraction of a second every century. Tides not only sculpt coastlines, but regulate spin, ensuring a dynamic interplay between celestial bodies. Similarly, Jupiter's gravitational pull stabilizes the orbits of its moons, synchronizing spin rates, preventing catastrophic collisions, and maintaining harmony across its system. Gravity is not a static force. It is a constant, invisible conductor, regulating motion across billions of miles. Step back, and the pattern becomes clear. Spin is everywhere because gravity demands it. From atoms to stars, planets to galaxies, angular momentum is conserved, redistributed, and amplified by gravitational interactions. Gravity does not invent spin, but it nurtures it, amplifies it, and shapes it into coherent structures. It ensures that the universe does not remain a static, featureless void. Instead, motion becomes an intrinsic, unavoidable property of reality. Gravity is the silent rule-maker, the ultimate enforcer of rotation. Without it, the universe would not dance. Stars would not shine in organized constellations. Planets would not rotate. Galaxies would dissolve into chaos. Spin is the signature of gravity's patient work, written across the cosmos in every orbit. every axis, every spiral. Even our own lives are shaped by gravity's orchestration of spin. The Earth's rotation creates day and night. The tilt of its axis gives us seasons. Ocean currents and wind patterns follow the subtle guidance of planetary spin. Our very biology, sleep cycles, hormonal rhythms, migratory instincts, is attuned to the motion gravity has imposed on our world. We are born into a universe where spin is inevitable, yet we rarely notice it. We walk on a rotating planet, orbit a rotating star, and dwell within a spinning galaxy. Our perception of stillness is an illusion. The universe moves beneath and around us in an unbroken ballet. Gravity's work is ongoing. Stars merge, galaxies collide, planets wobble, and black holes spin. Each interaction redistributes angular momentum, ensuring that rotation remains a universal constant. Even as the universe expands, stretching space itself, gravity continues to influence motion, binding clusters of galaxies, shaping cosmic filaments, and maintaining the delicate balance that allows everything to spin. From the smallest atom to the largest supercluster, gravity ensures that the universe does not stagnate. Spin is a fundamental outcome of its persistent, patient guidance. Gravity and spin are inseparable. One is the force that shapes, constrains, and redistributes motion. The other is the manifestation of that motion, the observable signature of a universe in flux. Every rotation, from electrons to galaxies, is a testament to gravity's influence. The universe is not random. It is a precisely choreographed dance. And in understanding gravity, we begin to understand why everything spins, why motion is not optional, why rotation is inevitable, why the cosmos itself is alive with energy in constant motion. Spin is the language, gravity is the teacher. Together, they write the story of the universe, one revolution at a time. The universe is a violent place. Not violent in the way we think of explosions or wars, but violent in its constant flux, in the ceaseless tug of gravity, in the collisions of particles, planets, stars, and galaxies. Yet, amid this chaos, one truth endures. Spin persists. Motion begets motion, and collisions, paradoxically, often preserve the very rotations they disrupt. In our imagination, a collision often evokes images of annihilation. Two planets smashing together, two stars merging, a meteorite striking Earth, catastrophe, chaos, obliteration. And yet, these cosmic collisions do more than destroy. They redistribute angular momentum, the cosmic currency of spin. Picture two clouds of gas hurtling toward each other. Each has its own rotation, perhaps slow, perhaps chaotic. When they collide, gravity and momentum interact. Some spin is cancelled, some amplified. Out of the wreckage, new structures form, a spinning disk, a newborn star, or a cluster of planets. Chaos, it seems, is just another way for spin to persist. Even our moon may be a product of such a violent origin. Scientists believe that a Mars-sized body collided with the early Earth, sending debris into orbit that coalesced into the moon. That cataclysm transferred angular momentum, tilting Earth's rotation and giving the moon its own locked spin. From destruction came an enduring, stable system of rotation. Spin is not easily destroyed. In physics, the law of conservation of angular momentum ensures that unless an external torque acts, rotation is preserved. Collisions may change the axis, the speed, or the distribution, but they rarely eliminate spin altogether. Even the most chaotic environments, supernovae, galactic mergers, or asteroid bombardments, cannot erase angular momentum. It is a stubborn law, written into the fabric of the cosmos, ensuring that motion continues even when structures are shredded or transformed. On smaller scales, the same principle holds. Asteroids collide, break apart, or are captured by planetary gravity. Their spins are altered by impacts, tidal forces, and radiation, yet rotation persists. The tumbling, spinning, chaotic paths of meteors in space are all evidence of this universal persistence. Consider the asteroid belt between Mars and Jupiter. Every fragment is spinning, tumbling, colliding, and reconfiguring. Some collisions fragment bodies, some create moons around larger asteroids, but angular momentum is never lost. It is transferred, redistributed, and conserved, a cosmic inheritance passed along each collision. On stellar scales, collisions are cataclysmic yet orderly in a strange way. Binary star systems often interact gravitationally, exchanging mass and momentum. When massive stars collide, they may produce even more massive stars, hypernovae, or black holes. And yet, the remnants spin. Pulsars, neutron stars, and black holes are extreme examples. The core collapse of a star can amplify spin rates astronomically, creating objects rotating hundreds of times per second. Collisions, instead of quelling spin, often create some of the fastest, most extreme rotations in the universe. Zoom out, and the story repeats. Galaxies collide in a slow-motion ballet spanning millions of years. Stars rarely collide directly. The distances are vast, but the gravitational interplay is dramatic. Angular momentum is redistributed, spinning galaxies merge, spiral arms twist, and elliptical galaxies are born. Even in chaos, the universe preserves motion. Galaxies that form from mergers carry the spin of their progenitors, imprinted in the motions of their stars. Cosmic collisions, it seems, are less about destruction and more about transformation. The energy is redirected, not erased. Rewind to the moments after the Big Bang. The universe was a hot, dense, roiling chaos of particles and radiation. Tiny quantum fluctuations created irregularities in density. Gravity amplified them. Spinning structures emerged naturally from this primordial turbulence. Even at the smallest scales, tiny rotations in gas and dark matter clouds seeded the formation of stars, planets, and galaxies. Chaos itself, in combination with gravity, created the persistent rotation we observe today. Spin is woven into the universe from its first moments. The persistence of spin is more than a curiosity. It shapes the architecture of the universe. Planetary systems, galaxies, and cosmic filaments all exist in patterns determined by conserved angular momentum. Take the solar system. The planets all orbit in roughly the same plane and direction, a consequence of their formation in a rotating protoplanetary disk. Even as collisions and gravitational nudges occurred, the fundamental direction and spin persisted. This coherence is why the solar system is not a chaotic mess, but a structured, predictable system. At first glance, the universe may appear chaotic. Collisions, explosions, and gravitational slingshots can scramble paths and velocities. But the underlying physics, gravity and angular momentum conservation, ensures order within the chaos. Spin is a memory of past interactions, a fossil record of collisions, gravitational tugs, and cosmic turbulence. Every rotation is a story, a record of what came before, encoded in the motion of planets, stars, and galaxies. Tides add another layer to this story. Gravitational interactions between objects gradually modify spin. Earth's rotation slows due to the moon's tidal pull. Planets in close orbit around stars often become tidally locked, rotating in sync with their orbits. Even as collisions and chaos shuffle matter, tidal forces can create new stability. Spin may change, but it rarely disappears. Gravity ensures that rotation is preserved, redistributed, and eventually harmonized across billions of years. Chaos is not an enemy of spin. It is a sculptor, a transformer, a teacher. Each collision, explosion, or gravitational tug writes a new line in the universal story of rotation. Angular momentum is never destroyed. It is transferred, amplified, and perpetuated. From meteors tumbling through space to galaxies swirling in their cosmic dance, the universe is a testament to the persistence of motion. Chaos does not erase spin. It refines it, reshapes it, and ensures that every structure, from the smallest asteroid to the largest galaxy, carries a signature of the forces that created it. Even on Earth, the principle resonates. Hurricanes, whirlpools, and cyclones form from chaotic systems, yet they rotate due to conservation of angular momentum and planetary spin. Even our weather, turbulent, unpredictable, carries the fingerprints of cosmic principles. Chaos is the universe's forge, and spin is the product. The storms, the eddies, the rotations around us all echo a truth that began billions of years ago in the primordial chaos. Motion endures, no matter the chaos. Chaos and collisions are inevitable. Destruction and turbulence are natural, yet spin persists, imprinted across scales, conserved through collisions, guided by gravity, shaped by tidal forces. Every rotation tells a story of violent beginnings, cosmic interactions, and the relentless persistence of motion. The universe is not still, it is a grand spinning testament to the power of physics, a story written in motion, preserved through chaos, and whispered across the eons. Spin is both the consequence of chaos and its enduring survivor. Wherever you look, from the smallest pebble to the largest galaxy, the universe remembers. Everything moves, everything rotates, and everything continues to spin. Before planets spun, before stars pirouetted in galaxies, before the colossal collisions of asteroids and comets reshaped motion across the cosmos, there was the infinitesimally small. There was the realm where reality behaves differently, where certainty dissolves into probability, and where the seeds of all cosmic rotation were quietly sown. This is the quantum world, the subatomic stage upon which the first whispers of spin emerged. Spin, at its most fundamental, exists even before the formation of matter as we know it. In quantum mechanics, particles possess a property called intrinsic spin, a kind of angular momentum that is inherent, built into their very existence. Unlike the rotation of a planet or a star, quantum spin isn't something that occurs in space. It is an intrinsic quality, a quantum signature encoded in the particle itself. Electrons, protons, neutrons all possess spin. It is quantized, meaning it comes in discrete, fixed values. Electrons, for instance, can have spin up or spin down. These labels may sound simplistic, but they are profoundly important. Spin determines how particles interact, how atoms bond, how matter organizes itself into molecules, and ultimately, how structures in the universe take shape. Without quantum spin, matter as we know it would collapse into chaos. Electrons wouldn't maintain their positions around nuclei, atoms wouldn't form stable structures, and chemistry, the very language of life, would be impossible. Spin, in essence, is the invisible thread from which the fabric of the universe is woven. It's easy to think of spin as just an atomic curiosity, but its influence scales up in surprising ways. Consider a cloud of gas and dust in the early universe, just after the Big Bang. On the smallest scales, random quantum fluctuations imparted tiny rotations to particles. Individually, these rotations were imperceptible, but collectively, they added up. Gravity, patient and relentless, began pulling matter together. As clouds contracted under their own weight, the tiny rotational motions were amplified. Conservation of angular momentum, the same law that governs spinning planets, ensured that the cloud's initial microscopic spin translated into macroscopic rotation. Out of the chaotic dance of particles, spinning stars, planets, and eventually galaxies were born. In this way, the universe's grand rotations are echoes of the quantum realm. Every spiral galaxy, every orbiting moon, every whirling hurricane carries the fingerprint of subatomic spin amplified over billions of years. Quantum fluctuations are another crucial piece of the puzzle. In the vacuum of space, even empty regions are not truly empty. Tiny energy fluctuations occur constantly, appearing and disappearing in compliance with Heisenberg's uncertainty principle. These fluctuations might seem trivial, but on cosmological scales, They provide the initial irregularities in density that seed the formation of structure in the universe. Where there is a density difference, gravity begins to act. And where there is a slight asymmetry, tiny rotations emerge. These early twists, born of quantum randomness, become the foundation for cosmic angular momentum. The universe, in its infancy, was chaotic, but the seeds of spin were already embedded in the quantum noise of creation. Spin also connects deeply to one of the universe's most fundamental concepts, symmetry. Quantum mechanics and particle physics rely on symmetries to explain why particles behave the way they do. Spin is tied to rotational symmetry in space. A particle with spin behaves differently when rotated in certain ways. It's a subtle, precise mathematical property that dictates the rules of the microscopic world. This is why quantum spin is not merely an abstract idea. It is a governing principle. It ensures stability in atoms, guides the formation of molecules, and ultimately constrains the shapes and rotations of macroscopic objects. Without it, there would be no planets, no spinning stars, no galaxies, no universe as we know it. Quantum spin is intimately connected to magnetism. Spinning electrons generate magnetic moments, tiny magnetic fields that, when aligned collectively, produce macroscopic magnetism. This is why the Earth has a magnetic field, why stars exhibit magnetic activity, and why the universe is permeated with magnetic structures spanning vast scales. Magnetic fields, in turn, influence rotation. Charged particles moving in magnetic fields experience forces that can alter their paths and even the spin of the matter they comprise. Stellar formation, accretion disks around black holes, and the dynamics of galaxies are all influenced by this interplay of quantum spin and magnetic forces. In essence, the universe's grand rotations are not just a mechanical accident. They are guided and shaped by the deep quantum rules that govern every particle. Spin at the smallest scale cascades upward, shaping the very motions of stars and galaxies. Beyond electrons and protons, the universe contains particles with more exotic spins: bosons, fermions, neutrinos, and hypothetical particles like gravitons. These spins determine how particles interact and how forces propagate across space. Consider neutrinos, nearly massless and incredibly abundant. Their tiny spin and rapid movement influence the distribution of matter on cosmic scales. During the early universe, neutrinos streamed freely, carrying angular momentum and energy, subtly shaping the formation of galaxies. Even invisible, ethereal particles like these carry the weight of cosmic rotation. On the largest scales, the universe itself exhibits a surprising coherence. Recent studies suggest that galaxies may exhibit preferred directions of rotation across vast stretches of space, hints that the early quantum fluctuations and primordial spin left an imprint billions of years later. The whisper of quantum spin may still echo in the rotations of galaxies across the cosmic web. Quantum mechanics adds another layer of wonder: entanglement. Two particles can share a spin state even when separated by light years. Changes in one's spin instantaneously affect the other, a phenomenon Einstein famously called spooky action at a distance. This means that, at a deep level, spin connects distant regions of the universe. The very property that gives rise to planets' rotations also links particles across unimaginable distances. This means that, at a deep level, spin connects distant regions of the universe. The very property that gives rise to planets' rotations also links particles across unimaginable distances. Spin is both local and cosmic, bridging the microscopic and the vast binding matter in motion across scales. There is another subtle connection. Spin is linked to the universe's arrow of time. As systems collapse, expand, and interact, spin governs how energy and momentum are distributed. It influences angular momentum transfer, how disks form around stars, how planets migrate, and how structures evolve. Spin ensures that motion has direction, that systems are not entirely chaotic, and that the universe's story unfolds in patterns rather than randomness. Even in entropy's relentless march, spin is a constraint, a hidden order in the apparent disorder. It is both a relic of the universe's quantum infancy and an active player in shaping cosmic evolution. It's astonishing to realize that every hurricane on Earth, every spinning carousel, every orbiting moon carries the legacy of quantum spin. The microscopic twitches of electrons and subatomic particles billions of years ago determined the rotations of planets and stars. Spin bridges scales, connecting our everyday experience to the deepest laws of physics. When we look up at the night sky and see stars rotating, galaxies spinning, and planets orbiting, we are witnessing the amplified whispers of quantum events. The universe is not random, it is a coherent structure, guided from the smallest scales to the largest by a single principle. Rotation is inevitable, conserved, and amplified. Spin is the thread that connects quantum uncertainty to cosmic grandeur. From the tiniest particles to the largest galaxies, from the chaotic birth of stars to the orderly dance of planets, spin endures. It is born of quantum fluctuations, amplified by gravity, shaped by collisions, and preserved through time. Without quantum spin, the universe would be silent, still, and featureless. With it, motion emerges, structure forms, and the cosmos becomes a tapestry of spinning, orbiting, and rotating matter. Every celestial motion, every whirl of a planet, every twist of a galaxy is a descendant of these first, imperceptible spins, echoing through billions of years. Spin is more than motion. Spin is heritage. It is the universe remembering its quantum beginnings, narrating a story written in rotations, from the subatomic to the cosmic, and from the chaos of creation to the intricate ballet of galaxies. Close your eyes for a moment and imagine the universe as a grand, infinite ballroom. Across this dark expanse, countless dancers whirl, some twirling solo, some locked in intricate embraces, and all obeying the unseen choreography of a force older than time itself: gravity. Gravity is the quiet conductor of the cosmic symphony, orchestrating a dance where every step, every spin, and every orbit follows a rhythm that began billions of years ago. Gravity is deceptively simple. Drop a stone, and it falls. Let go of a ball, and it rolls downhill. But in the grand scheme, gravity is nothing less than the universe's sculptor. It pulls gas into stars, binds planets into orbits, and shapes the spinning whirlpools of galaxies. Without gravity, there would be no cosmic rotation, no orbital dance, no celestial pirouettes. Think of a spinning top. When you spin it, it remains upright due to angular momentum. Now imagine that same top suspended in a field of invisible hands, all pulling it gently in different directions. That is gravity acting on a spinning celestial body. It doesn't just pull, it guides, stabilizes, and sometimes disrupts, ensuring that every spin and orbit becomes part of a greater, intricate ballet. Stars are born in clouds of gas and dust, sprawling nurseries called nebulae. These clouds are chaotic, turbulent, and uneven. Gravity causes the densest regions to collapse, pulling matter inward. As the gas contracts, it begins to spin. Why? Because angular momentum must be conserved. Tiny initial rotations, even from quantum fluctuations we explored earlier, get amplified as the cloud condenses. This spinning cloud flattens into a disk, a cosmic pancake where planets eventually form. Every planet inherits the spin of the original cloud, as though it's dancing to the same primordial music. Even the direction and speed of rotation are dictated by this early gravitational choreography. That's why most planets in our solar system spin in roughly the same direction, a signature of their shared birth. Rotation isn't just a solo act, it interacts with orbit. Gravity binds moons to planets, planets to stars, and stars to galaxies. But when two bodies exert mutual gravitational influence, something remarkable can happen: resonance. Resonance is a kind of cosmic choreography where spins and orbits lock into harmonious ratios. Jupiter's moons are a classic example. Io, Europa, and Ganymede orbit in a 1-to-4 ratio, a gravitational rhythm that keeps their paths stable for eons. This resonance doesn't just organize motion, it amplifies spin and tidal forces, reshaping planets' interiors, heating oceans and sculpting surfaces. Gravity, it seems, is not just a force, but a teacher of celestial dance, enforcing patterns across time and space. Gravity also produces one of the universe's most intimate dances, tidal locking. When a moon orbits a planet, gravitational forces stretch and tug on it. Over millions of years, these tugs slow its rotation until the same side always faces the planet, just like our moon does with Earth. Tidal locking is more than a curiosity. It's a subtle transfer of angular momentum from one body to another. Earth's day lengthens gradually due to the moon's pull. Jupiter's moons have been molded by tidal forces, heating interiors and driving geological activity. Gravity sculpts spin not just at birth, but throughout the lifetime of a celestial body. Spin, it seems, is never entirely free. It's always negotiating with the surrounding gravitational web. Gravity's influence extends far beyond planets and stars. Look up at the Milky Way, and you see a spiral galaxy, its arms elegantly twirling in a grand cosmic pirouette. But why do galaxies spin? The answer lies in the same principles that shape planetary rotation. Early in the universe, regions of slightly higher density attracted more matter. As matter fell inward, it gained angular momentum, spinning faster as it collapsed, just like a skater pulling their arms in. Over billions of years, these spinning clouds of stars formed flattened disks, stabilized by gravity. Spiral arms emerge as density waves, regions of higher star concentration moving through the disk, carrying stars along in a synchronized rhythm. Even on these colossal scales, the seeds of spin planted in the early universe dictate the choreography. Every star, every gas cloud, every orbiting dust particle participates in this gravitational dance, guided by the same forces that pulled the first atoms together. But gravity's choreography isn't always serene. Collisions between planets, asteroids, or even entire galaxies can disrupt spins, alter rotation rates, or tilt axes dramatically. These cosmic encounters are violent yet beautiful, creating new patterns and rhythms. Consider Uranus, spinning almost on its side. Evidence suggests a massive collision early in its history tilted its axis. Neptune's moon Triton, a captured object, spins in a retrograde orbit, evidence of gravitational capture. Even galaxies collide and merge, their spins twisting and tangling, creating elliptical galaxies from spiral ones. Gravity is both creator and destroyer, a force that stabilizes and destabilizes in equal measure, ensuring the universe's dance is never monotonous. Gravity reaches its most extreme near black holes. As matter spirals into these cosmic abysses, it forms an accretion disk, rotating at immense speeds. The black hole itself can spin, dragging space-time along in a phenomenon called frame dragging. Here, rotation and gravity become inseparable, a perfect illustration of how angular momentum persists even in the most extreme environments. A spinning black hole warps light, bends paths of particles, and can even power relativistic jets that shoot across galaxies. Spin, amplified and constrained by gravity, becomes one of the universe's most dramatic displays. Without gravity, spin would be chaotic, random, and fleeting. Gravity organizes, harmonizes, and amplifies. It channels the universe's angular momentum into coherent rotations, ensuring that stars, planets, and galaxies don't simply drift apart or collapse into disorder. Every rotation, every orbit, every celestial pirouette is a testimony to gravity's patient guidance. Even in the seeming randomness of cosmic collisions, spin obeys the laws of physics, conserving angular momentum, redistributing energy, and stabilizing the motions we observe billions of years later. Gravity doesn't just pull, it choreographs. As we look at the night sky, we may see stationary stars and planets from our limited vantage, but in reality, the universe is alive with rotation. Every object participates in a dance that began long before humans existed. Earth spins, the moon orbits, the sun rotates, the Milky Way spirals, all in response to the same gravitational rhythm that amplified tiny quantum spins into cosmic motion. Understanding this dance gives perspective. Our lives are brief, but the forces shaping them are ancient. Spin and gravity remind us that we are part of a larger narrative, a continuous flow of motion stretching from subatomic particles to the vast cosmic web. Every tornado, every hurricane, every orbiting satellite is connected to this grand, universal choreography. Gravity and spin are inseparable partners, from quantum fluctuations to galaxies, from planetary accretion disks to spinning black holes. Angular momentum and gravitational forces sculpt the universe. Spin alone would be meaningless without gravity's guiding hand, and gravity's power is magnified through rotation. Together, they create the cosmos we observe, a universe in constant motion, elegant, dynamic, and ever-turning. Every spinning planet, every orbiting moon, every twirling galaxy is part of this dance, a rhythm that has persisted for billions of years and will continue long after we are gone. Spin is the music, gravity is the conductor, and the universe is the grand ballroom where this eternal dance unfolds. Close your eyes and picture a figure skater gliding across the ice. She begins with arms outstretched, spinning slowly, then pulls her arms inward. Instantly, she spins faster. The law of physics she demonstrates is as old as the universe itself. Angular momentum, a principle so fundamental that it governs the motion of everything from falling leaves to galaxies. Angular momentum is the hidden rhythm behind the spinning universe. It's the silent law that prevents the cosmic dance from descending into chaos. It preserves the motion, ensures continuity, and creates the spinning patterns that define planets, stars, and galaxies. To understand why everything spins, we must understand angular momentum. Angular momentum is conserved. This means that unless an external force acts upon a system, its total spin remains constant. On Earth, it manifests in subtle ways. A gyroscope remains upright, hurricanes rotate in predictable directions, and planets rotate along axes that have persisted for billions of years. But on cosmic scales, conservation of angular momentum is nothing short of a universal decree. When a cloud of gas collapses to form a star, it spins faster as it shrinks. When a star dies and collapses into a neutron star, it can rotate hundreds of times per second. When galaxies collide, angular momentum is redistributed, creating spirals, bars, and elliptical galaxies. Every spin we observe is an echo of this ancient law. Nothing is created or destroyed. It is merely transferred, transformed, and amplified. To see angular momentum in action, look at the tiniest scales. Particles in quantum physics possess intrinsic spin. Electrons whirl around their axes, protons spin in atomic nuclei, and even photons carry angular momentum. These microscopic spins don't just stay small. In the chaotic early universe, these tiny rotations, when amplified by gravitational collapse, seeded the spins of entire solar systems. On larger scales, storms on planets are guided by the same principle. Hurricanes on Earth rotate because of the Coriolis effect, a consequence of the planet's spin. Even as water and air flow in complex, turbulent patterns, the conservation of angular momentum imposes order, shaping spirals and vortices that mirror the grand designs of galaxies. Now scale up. Imagine a protoplanetary disk, a vast pancake of gas and dust orbiting a newborn star. Initially, it may rotate slowly, almost imperceptibly. As gravity pulls matter toward the center, the disk contracts. Conservation of angular momentum demands that the spin speed increase. This is why planets rotate, often rapidly. Jupiter spins once every 10 hours. Saturn rotates in just over 10 hours as well. Earth takes 24 hours. Mars about 25. Each planet's spin is a fossil record of the disk from which it formed, a preserved snapshot of the early solar system's motion. The conservation of angular momentum is like a cosmic time capsule, embedding history in the very rotation of worlds. Spin isn't just a curiosity, it stabilizes planets. Without rotation, Earth would have no day-night cycle, no equatorial bulge, and a much less stable climate. The tilt of our axis, caused by gravitational interactions with other planets, gives us seasons. Even the Moon's synchronous rotation, a product of tidal locking, is an outcome of angular momentum exchange. Gravity and angular momentum are partners in an intricate dance, exchanging energy and shaping orbits and spins over billions of years. When Jupiter tugs on its moons, or Earth tugs on the Moon, the spin of each is subtly altered. The system remains in balance, a delicate equilibrium written in the language of physics. Angular momentum is not limited to individual planets or stars. Entire galaxies rotate, and their spins can reveal the history of cosmic evolution. Spiral galaxies, like our Milky Way, owe their flat disks and sweeping arms to the initial angular momentum of the primordial gas clouds that formed them. Even clusters of galaxies display rotation. When massive structures merge, angular momentum is redistributed, shaping cosmic filaments, walls, and voids. The universe itself seems to remember every rotation, conserving momentum across unimaginable distances and epochs. At the most extreme end, angular momentum shapes black holes. When a massive star collapses, its core spins faster, conserving the angular momentum it inherited from its progenitor. Spinning black holes warp spacetime, twist magnetic fields, and power relativistic jets that shoot across galaxies. Angular momentum in these contexts is both destructive and creative. It channels energy into jets, shapes accretion disks, and even influences the orbits of nearby stars. Spin is not merely rotation, it is the engine of cosmic phenomena, converting mass into motion, motion into energy, and energy into observable marvels. Even the universe as a whole may carry angular momentum. Large-scale motions of galaxy clusters, rotations of cosmic filaments, and flows of dark matter suggest that the conservation of angular momentum operates on scales far beyond our immediate perception. Some cosmologists theorize that primordial rotations in the early universe could have influenced the distribution of matter, seeding the patterns we see today. Spin, in this sense, is not just a property of objects. It is a fundamental feature of space-time itself, woven into the very fabric of the cosmos. For humans, the implications are profound. Every rotation we see, the Moon orbiting, the Sun spinning, Earth turning, is governed by principles we can describe mathematically, but that extend far beyond our intuition. We are participants in a system where motion is eternal, a universe where energy and spin cannot be destroyed, only transformed. Understanding angular momentum connects us to cosmic history. It allows us to read the fingerprints of the universe, from the fastest pulsars to the slowest drifting nebulae. When we look up at the night sky, every star, every planet, every galaxy is spinning because of laws that have persisted since the Big Bang. We are witnessing motion that is older than life itself, encoded in the simplest yet most powerful law of physics. Angular momentum is the universe's memory. Every rotation, from the tiniest electron to the largest galaxy, preserves history. It ensures continuity, stability, and cosmic order. It explains why planets spin, why galaxies rotate, and why everything, from atoms to black holes, twirls in a dance dictated by an immutable law. The next time you watch a leaf spiral to the ground, a hurricane form, or the stars drift across the night sky, remember, you are witnessing the echoes of angular momentum, a force as fundamental as time itself, shaping everything we see, from the smallest whirl to the grandest spiral in the heavens. Spin is not random. It is conservation made visible, a testament to the universe's ancient choreography, a cosmic dance written into the laws that have governed reality since the very beginning. Close your eyes And imagine the universe as a vast billiard table stretching across incomprehensible distances. Galaxies, stars, planets, and asteroids are the balls, and gravity is the cue that sends them careening across space. Every impact, every near miss, every gravitational nudge shapes the spin of celestial bodies. Rotation in the universe is rarely gentle or uniform. It is sculpted by chaos, collisions, and cosmic violence. The universe, in many ways, is defined by these encounters. Nothing forms in perfect isolation. Stars collide in clusters, galaxies merge in cataclysmic embraces, and planets are bombarded by asteroids and comets. These interactions transfer angular momentum, alter rotation speeds, tilt axes, and sometimes even flip entire planets upside down. To understand why everything spins the way it does, we must understand the power of cosmic collisions. Picture a newborn star, surrounded by a swirling protoplanetary disk of dust and gas. Within this disk, particles collide constantly. Some stick together, gradually forming planetesimals, while others shatter and scatter. Each collision subtly alters the spin of the growing object. If two planetesimals collide off-center, the resulting body will start to rotate. If the collision is head-on, it may spin slowly or barely at all. Over millions of years, countless collisions shape the eventual rotation of a planet. The direction, speed, and tilt of its spin are a direct record of this chaotic birth. Earth, for example, is thought to have experienced a giant collision with a Mars-sized object early in its history. This colossal impact not only gave rise to the Moon, but also imparted much of Earth's current rotation. Without this violent event, the length of our day and even the tilt of Earth's axis, which gives us seasons, might have been completely different. Spin is, in this sense, a fingerprint of chaos. Even after planets form, collisions continue to influence rotation. Asteroids and comets slam into planetary surfaces, sometimes altering spin speeds or axis tilt. Some impacts are subtle, gradually shifting rotation over eons. Others are dramatic, capable of flipping a planet's spin or drastically slowing it down. Mercury, for instance, has a unique rotational resonance. It rotates 3 times for every 2 orbits around the Sun. This unusual spin is a result of both solar tidal forces and ancient impacts that nudged it into this locked pattern. Venus rotates backward relative to most planets, a retrograde spin likely caused by massive collisions early in its history. These spins are not random. They are records of cosmic chaos etched into planetary motion. Collisions are only part of the story. Gravity continues to shape rotation long after the dust has settled. Tidal forces, caused by the gravitational pull of nearby bodies, act like cosmic brakes and accelerators. They can slow rotation, lock a planet in synchronous rotation, or even gradually change the tilt of its axis. The Moon, for instance, is tidally locked to Earth, always showing the same face. Earth's rotation is slowing down by about 1.7 milliseconds per century due to lunar tides. In a few 100 million years, the length of a day could be noticeably longer. Tides are subtle, slow, and inexorable, a form of rotational shaping that occurs not with violence, but with patient persistence. On much larger scales, collisions between galaxies create the most spectacular rotations in the universe. When 2 galaxies approach, their stars rarely collide directly. The distances are too vast, but their gravitational interactions pull, stretch, and twist each galaxy. Spiral arms are formed, bars emerge, and the overall angular momentum is redistributed. These cosmic dances are violent yet elegant. The Milky Way itself is a product of countless mergers, absorbing smaller galaxies over billions of years. The stars we see twirling in the galactic disk carry the memory of these collisions, each orbit shaped by past interactions and the subtle redistribution of angular momentum. The cosmos is not deterministic in the sense that every spin can be predicted from first principles. Chaos theory tells us that small differences in initial conditions can lead to wildly different outcomes. Two nearly identical planetary systems could evolve entirely differently if a few collisions occur at slightly different angles. This sensitivity is why the diversity of spins in the universe is so staggering. Venus rotates retrograde. Uranus spins on its side. Jupiter rotates rapidly on a nearly perfect axis. Every oddity is a testament to the chaotic history of formation and collision, showing us that randomness and physics are partners in creating cosmic order. Scientists can read the history of collisions in many ways. Crater counts on planetary surfaces reveal bombardment histories. The orientation of planetary axes hints at ancient impacts. Debris rings around stars, asteroid belts, and even the composition of planets themselves tell stories of violent beginnings. Our own moon is a giant cratered record, a testament to early solar system chaos. Mars's hemispheric dichotomy, the stark difference between its northern lowlands and southern highlands, may be evidence of a colossal ancient impact. Even Earth's continents carry scars of collisions, not just from meteorites, but from the slow tectonic convergence that forms mountains and reshapes the surface. At the extremes, black holes provide dramatic examples of rotational chaos. When two black holes merge, their spins combine in ways that can produce powerful gravitational waves. LIGO and Virgo have detected these ripples in spacetime, revealing not only the existence of black holes, but also their past histories of spin and collision. The resulting black hole can spin faster or slower, tilted at odd angles, depending on the orientation of its progenitors. Even in the darkest corners of the universe, collisions leave indelible marks on rotation, showing that spin is a record of past events on scales both vast and extreme. From tiny dust grains to massive galaxies, collisions and chaos are essential to rotation. The universe did not need to spin everything uniformly. It simply followed the laws of physics. Conservation of angular momentum ensures that spin is preserved, while collisions and tidal forces modify it, creating the diverse, intricate rotations we observe. Chaos is not destructive randomness. It is a sculptor, carving motion out of the primordial mess, guiding planets, stars, and galaxies into rotational patterns that endure for billions of years. Each spin, each tilt, each retrograde rotation is a cosmic story, a narrative of collisions, mergers, and gravitational negotiations. When we look at the planets, the stars, or even the debris around distant exoplanets, we are reading the diary of the cosmos. Spin is the handwriting. Collisions are the punctuation. Chaos is the narrative voice. Understanding these interactions gives humanity a sense of cosmic continuity. Every rotation we see is not random, it is history in motion. Every tilted axis or retrograde spin tells us about the violent processes that shape the universe, often billions of years before life existed on Earth. The universe spins not just because of intrinsic laws, but because of its history of chaos. Collisions, impacts, and tidal forces have sculpted the motion of planets, stars, and galaxies. Angular momentum preserves the memory of these events, while chaos ensures diversity and rotation. Every spin is a testament to the interplay of violence and order. The cosmic ballet continues, shaped by ancient collisions and ongoing gravitational interactions. The spins we observe, from Earth's gentle rotation to the furious whirl of a neutron star, are the legacy of a universe where chaos and law coexist, producing motion that endures across eons. Close your eyes for a moment and imagine the universe not just as a collection of stars and planets, but as a vast, invisible web of magnetic energy stretching across galaxies, threading through nebulae, and whispering to every charged particle that floats through space. These magnetic fields are unseen, yet their influence is profound. They shape the spin of stars, guide the formation of planets, and even affect the rotation of entire galaxies. To understand why everything spins, we must look beyond collisions and gravity and into the subtle, omnipresent force of magnetism. From the moment a cloud of gas begins to collapse into a star, magnetic fields are at work. These clouds, called molecular clouds, are not uniform. They are threaded with weak magnetic lines, stretching across light years. As gravity pulls the cloud inward, the magnetic field lines are dragged along, twisted, and intensified. This twisting acts like a brake and a guide at the same time. Gas moving perpendicular to the magnetic field encounters resistance, slowing its collapse along certain axes. But along the field lines, gas flows more freely. This channeling of motion helps determine the rotation axis of the forming star and its surrounding disk. Without magnetic fields, stars might spin far faster, and disks might fragment chaotically, creating fewer planets or altering their orbits entirely. In this sense, magnetism is an architect, invisible yet decisive, subtly shaping the rotational blueprint of the cosmos. Consider a protostar, a newborn star forming at the heart of a collapsing cloud. Gravity is relentlessly pulling material inward, but as the star accretes gas, it also inherits angular momentum. Without regulation, the star would spin so fast it could tear itself apart. Enter magnetic braking. Magnetic fields, coupling with charged particles in the surrounding disk, act like a cosmic brake system. They transfer angular momentum away from the star, slowing its spin while allowing material to settle into the surrounding protoplanetary disk. The result is a delicate balance. The star spins steadily, the disk forms planets, and the universe preserves angular momentum on multiple scales. Our own sun's rotation is a testament to this process. It spins once every 27 days at its equator, slow enough to avoid disruption, thanks to billions of years of magnetic regulation. Even today, the solar wind, guided by magnetic fields, continues to carry angular momentum away from the sun, gradually slowing its rotation over eons. Magnetism does more than slow rotation. It also aligns spins. Observations of young star clusters show that stars tend to spin in directions correlated with the magnetic field of their parent molecular cloud. The cloud's magnetic field imprints its direction on the stars that emerge, creating large-scale patterns of rotational alignment across vast regions of space. This alignment extends beyond individual stars. In some star-forming regions, entire planetary systems show spin axes pointing in roughly the same direction as their neighboring stars. The invisible scaffold of magnetism dictates the orientation of worlds before they even fully exist. Zooming out to galactic scales, magnetic fields continue to play a decisive role. Spiral galaxies, like our Milky Way, are not random assemblages of stars. They exhibit large-scale, coherent magnetic fields that wrap along the spiral arms. These fields influence the motion of ionized gas, shaping the spin of gas clouds and regulating star formation. Interestingly, the magnetic field can even affect the rotation curve of a galaxy. While dark matter accounts for much of the gravitational behavior, magnetohydrodynamic forces provide additional torque on charged particles, subtly redistributing angular momentum across galactic disks. The spiral pattern itself, the iconic whirl of stars and dust, is in part a magnetic dance writ large. Planets too are influenced by magnetic forces. Early in a planet's formation, charged particles in the protoplanetary disk interact with magnetic fields, generating currents that influence rotation rates and axial tilt. On Earth, the dynamo action in the molten outer core generates our magnetic field, which in turn stabilizes rotation over geological timescales. Mars, by contrast, lost its global magnetic field billions of years ago. Without that stabilizing influence, its rotation axis wobbled more dramatically, contributing to climatic instability and the eventual loss of surface water. Venus's slow retrograde rotation may also be linked, in part, to ancient interactions with solar magnetic fields and tidal forces, showing that magnetism can subtly nudge even the slowest spins. Some of the most extreme examples of magnetic influence come from neutron stars and pulsars. Born in supernova explosions, these ultra-dense remnants often rotate hundreds of times per second. Their magnetic fields, billions of times stronger than anything we can imagine on Earth, dominate the behavior of surrounding plasma, funneling energy and matter along magnetic poles. These fields not only regulate rotation, but create the periodic beams of radiation that make pulsars detectable across the galaxy. The spin and the magnetic field are intimately linked. The very existence of pulsars as cosmic lighthouses is a result of this coupling. Magnetism is not a recent phenomenon. It has been present since the universe's earliest epochs. Primordial magnetic fields, generated in the first few million years after the Big Bang, may have influenced the rotation of the very first stars and galaxies. These ancient fields left imprints on the cosmic microwave background and may still influence galactic spins today. In this way, magnetism connects the smallest particles to the largest structures. From the swirling gas around a newborn star to the rotation of entire galaxies, magnetic fields are a subtle but persistent force shaping motion across cosmic time. Unlike gravity or collisions, magnetism is intangible, invisible to the eye, yet it sculpts motion with a precision that spans light years. It aligns, brakes, accelerates, and stabilizes rotation, turning chaos into coherence. It ensures that stars spin steadily, planets rotate predictably, and galaxies maintain their elegant spiral forms. Even as astronomers measure light, gravity, and motion, the underlying magnetic scaffolding quietly guides the cosmic dance. Every spin we see carries the fingerprints of these invisible lines, a reminder that the universe is as much defined by hidden forces as by the matter we can observe. By the time we look at a spinning planet, a whirling star, or a spiral galaxy, we are reading more than geometry. We are reading the memory of invisible fields, the subtle influence of forces that have guided motion for billions of years. Magnetic fields, entwined with gravity and collisions, ensure that rotation is not just a relic of the Big Bang, but an ongoing dialogue between matter, energy, and time. The spins we observe today, from gentle planetary rotations to furious stellar whirl, are partially invisible narratives written in magnetic ink. They remind us that the universe is not just a collection of objects, but a network of forces, visible and unseen, weaving motion into the very fabric of existence. Pause for a moment and imagine the universe not as a static backdrop, but as a living, turning, ever-evolving tapestry. Every particle, from the smallest electron to the largest galaxy cluster, carries motion. Spin is not a local phenomenon. It is cosmic, timeless, and fundamental. As we reach the final chapter of our journey into why everything spins, we confront a deeper question. Why does motion persist, and why does it seem endless? To understand perpetual motion on a cosmic scale, we must journey back to the very beginning, the first fractions of a second after the Big Bang. Space itself was born from a singularity, a point of infinite density, expanding outward in every direction. In this explosive moment, matter, energy, and space-time emerged, but they did so with tiny irregularities, quantum fluctuations, minute asymmetries, subtle twists. These initial fluctuations were chaotic, but they were not perfectly still. Tiny variations in density and pressure imparted angular momentum to the matter, forming the first clouds, stars, and galaxies. Even the most minuscule spin in the primordial soup would be magnified over billions of years through gravitational collapse, magnetic forces, and interactions between celestial bodies. In essence, the universe inherited its spin from birth. Motion, rotation, and angular momentum are encoded into the cosmos itself, as fundamental as light or gravity. Once motion begins in a frictionless, near-perfect vacuum, it is extraordinarily difficult to stop. The universe is, in this sense, a self-spinning machine with no off switch. At the heart of every spin lies a simple yet profound principle: the conservation of angular momentum. It is a law so fundamental that it transcends galaxies and atoms alike. Angular momentum cannot be created or destroyed in an isolated system. It can only be transferred or redistributed. This principle explains why galaxies rotate, why planets spin, and why stars whirl. As a cloud collapses under gravity, its size decreases, and to conserve angular momentum, its spin rate increases. The same law governs a figure skater pulling in her arms to spin faster, or a neutron star spinning hundreds of times per second. Angular momentum is a cosmic echo of the universe's birth. Once imparted, it persists, passed down from one generation of stars to the next, and from one galaxy to another, creating a universe where everything, literally everything, is moving. Zoom out from a single star to a galaxy, and the magnitude of spin becomes staggering. Spiral galaxies, with their grand sweeping arms, are the universe's most elegant dancers. Each star orbits the galactic center, yet the combined motion of billions of stars follows a coherent rhythm. Here's the astonishing part. Galaxies don't spin randomly. Observations reveal that in many regions, spins are aligned on scales of tens or even hundreds of millions of light years. This suggests a deep underlying order, seeded by the initial conditions of the universe, amplified by gravity, and maintained over eons. Even galaxy clusters, enormous collections of galaxies bound by gravity, exhibit rotational patterns. These spins are ancient, fossilized from the earliest cosmic tides and flows. The universe is a swirling layered dance where spin echoes across time and space, linking galaxies that will never collide, yet seem choreographed by some invisible hand. Rotation is not just spatial, it has a temporal component. As systems spin, they define time through motion. Planetary rotations create days, orbital periods create years, and pulsars act as celestial clocks, ticking with incredible precision. Motion gives structure to time. Even the expansion of the universe, the stretching of space itself, is not entirely isotropic. Tiny anisotropies and rotations in the cosmic microwave background, the afterglow of the Big Bang, reveal that the universe has retained memory of its primordial spins. Time and motion are entwined. Spin is not merely movement, but a cosmic heartbeat, marking the passage of billions of years. Why does motion persist across cosmic time? The answer lies in the near-perfect emptiness of space. In the vacuum of interstellar and intergalactic space, there is minimal friction. Particles and celestial bodies can move almost indefinitely, unimpeded by resistance. Once a planet spins, a star rotates, or a galaxy swirls, nothing in the vacuum of space can easily stop it. Even when interactions occur, collisions, tidal forces, or magnetic braking, motion is never destroyed, it is redistributed. Angular momentum may shift from one object to another, from one star to its orbiting planets, from one galaxy to its satellites, but it does not vanish. The universe is a perpetual motion engine, fueled by its own birth and maintained by its inherent laws. Among the most extreme examples of enduring spin are black holes. Formed from the collapse of massive stars or the merging of smaller black holes, these objects carry enormous angular momentum. Some spin near the speed of light, warping space and time itself in a phenomenon known as frame dragging. Black holes can even impart rotation to the surrounding space-time, forcing nearby matter into aligned orbits. In this way, a black hole is not merely a gravitational well, but a cosmic gyroscope, preserving motion over billions of years. The spin of black holes is a testament to the universe's ability to conserve angular momentum in the most extreme conditions imaginable. If we take the largest possible view, the universe itself, we see that spin might never truly end. Galaxies move, clusters rotate, cosmic filaments flow, and the universe continues to expand. While the ultimate fate of the cosmos, whether it will collapse, expand forever, or fade into heat death, remains uncertain, the motion within it is remarkably persistent. Even in a dark, cold universe, spin endures. Angular momentum is woven into the fabric of existence. Stars may die, galaxies may merge, but the momentum of their motion is redistributed, ensuring that the cosmic dance continues, in one form or another, for eons to come. Everything we've seen, from the spinning electrons that generate magnetism to the whirling galaxies across billions of light years, speaks the same language: spin. It is a universal constant, a principle written into the laws of physics. Motion is the grammar of existence, rotation its most eloquent sentence. Through spin, the universe tells its story. It is encoded in the orbits of planets, the tilt of moons, the spiral arms of galaxies, and the magnetic heartbeat of stars. Motion is not random. It is a narrative, flowing from the first moments of creation to the present, stretching toward the distant future. So, why does everything spin? It is the legacy of the Big Bang, the immutable law of angular momentum, and the guiding hand of invisible forces like gravity and magnetism. It is the universe's way of organizing itself, preserving energy, and marking the passage of time. Spin is eternal, pervasive, and profound. It connects the microscopic to the cosmic, the first particles to the largest structures, and every moment of time to the next. To look at a spinning planet, a twirling star, or a spiraling galaxy is to witness the poetry of the cosmos, a dance that began billions of years ago and will continue long after we are gone. In the end, the universe is spinning because it must. Spin is motion made fundamental, the pulse of creation, the signature of existence itself. And as long as the laws of physics endure, the dance will never end.